Welcome back to Introduction to Geology. I'm Dr. William Patterson. Today we're going to talk about rocks and minerals, and particularly the classes of rock-forming minerals. So we're going to start out with the big ones, the silicates. These are all based on this fundamental unit, the silicate ion, SiO4. Now the silicate ion forms a tetrahedra with oxygen ions at the apices. When you put these together in a three-dimensional structure, in this case the quartz structure, you get a tetrahedron linked by oxygens to adjacent tetrahedra. Adjacent tetrahedra, tetrahedra below, all adjacent tetrahedra are linked in the same way. This results in a pure, relatively hard mineral. This is quartz. It's a silicate or SiO2 polymorph. A polymorph, in turn, is a mineral with the same chemical composition but a different internal structure. So the way these are organized relative to one another is going to determine the particular polymorph of SiO2. Tetrahedra are the basic building blocks of all silicate minerals. Approximately 95% of Earth's minerals are silicates. So it's very likely that when you pick up a rock anywhere on Earth, it's going to be a silicate. 95 chances out of 100, it should be a silicate. So now we need to classify these silicate minerals based on how the tetrahedra are linked. The most simple are the isolated silica tetrahedra. These are also called island silicates or inosilicates. Our example here is the mineral olivine. These consist of SiO4 basic units interspersed between magnesium and iron ions. And the result is no cleavage. There's no primary plane of weakness in this mineral because of these isolated island tetrahedra. Next up are single chain linkages. We're going to link these simple tetrahedra into a chain by sharing an oxygen at one corner of the tetrahedra. This is the pyroxene group, exemplified by the mineral azurite here. This is an iron, magnesium, calcium, sodium, aluminosilicate. It has two planes of cleavage at 90-degree angles. By linking these single chains together, we form double chain minerals, such as the amphibole group. And this one is exemplified by the mineral hornblende, a very common amphibole. You'll see it in almost any igneous rock you look at. It's going to be a little black, needle-like or pencil-shaped crystals you'll see in a common granite, for instance. So this double chain silicate results in two planes of weakness, which produce cleavage at 60 and 120 degree angles. Sheet linkages link double chains together, and the result is a vast sheet of linked tetrahedra. This vast sheet can be dark colored, such as in the mineral biotite here. This is black because of the presence of magnesium and iron. We have the alternative form, muscovite, seen here, which is usually a yellow or bronzy or clearish kind of look. And this is because instead of the magnesium and iron, it has aluminum and potassium. So this is hence a light-colored mica. Again, very common. Both of these are common in granites. Framework silicates link these tetrahedra together in a three-dimensional array. And this results in potassium feldspars known as orthoclase, which have obviously potassium and aluminum and the silicates made up of potassium aluminum silicate, which gives it this fairly light color. Alternatively, plagioclase feldspars can be dark colored. They can be black if they contain predominantly calcium. We call that a northite or northocite, the rock. Or if we're the sodium-rich end member, we have a white mineral called albite. These have two planes of cleavage at 90-degree angles. And then quartz, which is pure SiO2, give or take some trace elements that might make it purple. This is going to have no cleavage. These crystals have no cleavage. They have a particular type of fracture that is diagnostic, but no cleavage. How about some examples? Silicate classifications with examples here. We'll start out with isolated tetrahedra. These are linked by the bonding of each oxygen ion of the tetrahedra to a cation. These cations in turn bond to the oxygen ions of other tetrahedra, thereby isolating the tetrahedra from one another by cations on all sides. The example here, the best example there is, the most common example, is the mineral olivine. Almost always a greenish color, could be very, very dark green, almost black. This is common in the rock we call basalt that makes up Hawaii and the island of Iceland. Single chain structures are formed by the sharing of oxygen ions. Two oxygen ions in each silicate tetrahedra bond to adjacent tetrahedra in an open-ended chain. Goes on forever. These single chains are linked to other single chains by cations. And our example here is the mineral enstatite, a fairly common pyroxene. And sometimes this can be used as a gemstone. Not very often. You don't hear many people talking about their pyroxene rings, but it does happen. Double chain structures. Two single chains combine to form double chains linked to each other by shared oxygen ions. Adjacent double chains linked by cations form the structure in the amphibole group. Our example here, again, is hornblende. It's an extremely common amphibole. It has this characteristic shape when found in igneous rocks, and in large isolated crystals can look like this. Sheet structures. Each tetrahedra shares 3 of its oxygen ions with adjacent tetrahedra to build stacked sheets of tetrahedra. The cations may be interlayered with tetrahedral sheets. Micas and clay minerals are the most abundant of the sheet silicates, found everywhere. Clays are generally sourced from the weathering, the chemical weathering of feldspars, which we'll get to in a few minutes. Muscovite is a common sheet silicate, as is the clay kaolinite, found everywhere. The feldspars here in this granite are going to break down to become kaolinite. This muscovite here can also break down to form clays. Tectosilicates, also known as the framework silicates or the 3D silicates, are three-dimensional frameworks where each tetrahedra shares all of its oxygen ions with other tetrahedra. The most abundant framework silicates and the most abundant minerals in the Earth's crust are these minerals, these feldspars. Another common framework mineral we've talked about several times is the mineral quartz. These silicates can be very simple with only silicon and oxygen, or you can sprinkle in some sodium, calcium, potassium, magnesium, iron, etc. We saw in the case of amethyst, a tiny amount of iron can produce a dramatic change in the appearance of the crystal, the appearance of the mineral. The basic chemistry is very much the same in the purple variety versus the clear variety. Again, it's just a tiny amount of iron that gets emplaced by radiation. Carbonates contain the carbonate ion, CO3, as the basic building block. The carbonate ion consists of a carbon ion surrounded by and covalently bonded to 3 oxygen ions in a triangular relationship. Groups of these triangles are layered like sheets bound together by layers of cations. In the case of calcite, the cations are calcium 2+. Some examples seen here: aragonite, CaCO3, same chemistry as calcite, CaCO3. So these are polymorphs of CaCO3. Other examples include iron carbonate, siderite, dolomite, a calcium magnesium carbonate, very, very common. Azurite is a copper hydroxide carbonate. Malachite is a copper hydroxide carbonate. And magnesite is a magnesium carbonate. These are all fairly common carbonate minerals. Oxides are minerals in which oxygen ions are bonded to cations. Usually metallic ions like iron 2+ and iron 3+, iron 2+ being a little bigger than iron 3+, so that determines which goes into a particular crystal lattice. Most oxides are ionically bonded. Oxides are very important as a source of metals, such as the mineral hematite, as a source of iron. Hematite has a formula of Fe2O3. This is known commonly as rust. Magnetite has a formula of Fe3O4. This has magnetic properties. Limonite is a hydrous iron oxide. It's kind of powdery, orangey, yellowish color, very common. Corundum is a very hard aluminum oxide that in some cases has a gem quality variety called ruby. Other cases has a gem quality variety called sapphire. And bauxite is one of our more important sources of aluminum ore. It's an Al2O3 with water, so it's a hydrous aluminum oxide. And moving on to the sulfur-based minerals, sulfides are made of the basic sulfide building block, S2-, bonded to metallic cations. Most of these minerals are opaque and look like metal. Starting with galena, lead sulfide, a very silvery metallic luster. Chalcopyrite, a minor ore of copper, has this golden metallic luster. Sphalerite, the primary ore of zinc, has a resinous luster. Molybdenite has a metallic luster, primary ore of molybdenum. Pyrite, usually a brassy metallic color, is a minor ore of iron, really basically irrelevant ore of iron. Bornite is a minor ore of copper. It generally has this peacock appearance to it. Arsenopyrite is an ore of arsenic, and it has a metallic luster as well. Stibnite is an ore of antimony, and it has primarily this prismatic appearance or prismatic habit when you find it out in the wild. Sulfates, on the other hand, consist of minerals made of the sulfate ion, which is a sulfur surrounded by 4 oxygens. Gypsum is our primary example here. It's a calcium sulfate with water included in the lattice. Now, gypsum and anhydrite only differ by the presence or absence of water, hence the name anhydrite. Barite commonly appears in this desert rose habit. It's also identified easily by its very high specific gravity. And last but not least, celestite, a strontium sulfate.